Our story does not start with Plato, but 150 years earlier, some 2,500 years ago, with a more shadowy, legendary figure. We all learnt his name at school, but were given no idea of his importance. His name is Pythagoras. Exiled Romanian Shapti Unguru, professor of the history of mathematics at Tel Aviv University, revisits Crotone, a town in southern Italy, once a major city in Greater Greece.
As I left Romania, I used the first available opportunity to come to Crotone, the actual place in which the master organized his school and developed his ideas. It was here that Pythagoras came up with one of the most incredible and absurd, and yet one of the most powerful and fruitful ideas, without which Western thought, the way we know it, is inconceivable. The crucial Pythagorean idea consisted in the view that the material world is actually made up, constructed out of numbers, and that the proper way to understand it is to unravel the numerical relationships lying at the essence of things.
In an age of computers and checkout tills, accountants and commodity brokers, to say that all is number is a very different thing than it was for Pythagoras. For us, numbers are mundane, prosaic, matter of fact. They're tools that help us deal with things, instruments that help us measure and count and manipulate the world around us. For Pythagoras, numbers had almost magic powers, for they held the secret of the universe. They were no less than the very essence of the world.
And it is because we are Pythagoras' children, steeped into his ways of thinking, that it is quite impossible to conceive ourselves in a world for which the Pythagorean patterns of explanation are unavailable to us.
Pythagoras' claim that the world was based on numbers was unlike anything anyone had said before. There had, of course, been religious myths before the Greeks, but no one had tried to give an explanation, a theory of the world. Yet here was an account of the world that described it in terms of an abstract, theoretical notion. Other Greeks had suggested the world was made of water or fire, but you could not point to numbers. You could not find them in the world. It seemed they lay outside of the physical world. Little wonder, then, that for Pythagoras, they were sacred and mystical. Pythagoras was born on the Greek island of Samos, off the coast of Turkey, at the time of the tyrant Polycrates, and is said to have traveled to Egypt before settling in Italy, where he established his own community in Crotone, where it is claimed for a time he ruled the city. His world was, of course, very different from ours. It was a primitive society, lacking technical prowess. But it is not the material differences that separate us from him, but the way we think. According to an ancient legend, one day Pythagoras was passing a blacksmith's, and it occurred to him that the notes made by the hammers against the anvil seemed to vary with the size of the hammer. On returning home, he is said to have tried this out, comparing the notes from different lengths of string, and concluded that if musical notes were numerical, perhaps the world was also. Jocelyn Godwin teaches music at Colgate University in New York State. He believes that Pythagoras' discovery not only led Pythagoras to the conclusion that the world was number, but has provided us with the basis of all music.
I imagine him discovering it like this. He takes a string, let's say a string 2 feet long, this string, and he asks himself, what is the simplest mathematical operation I can do with this string? Cut it in half. What does a string 1 foot long sound like? And if you listen to the relation of those two notes, you hear something very familiar. You hear an octave. What you have there is the framework in which music can happen. So how does it happen? We imagine Pythagoras taking the next step. He divides his string in 3.
And the resulting note produced by this length of string is higher again than the octave by an interval which we call the perfect fifth.
But you can really make music with a perfect fifth, which you can't with an octave. For example, I can take a chain of perfect fifths, like this. I take those 7 fifths and I pack them together within a single octave, and what do I get? The scale that we know, the white notes of the keyboard, are derived from that very simple mathematical operation of dividing a string into 3. So Pythagoras found that out of the fifths are made the scale, the basis of all melody.
I heard a goose pimples ran up my skin. I said, hi, how you doing? And how have you been? She said, I'm doing fine. I hope you're doing the same. Do you know who I am? Yeah, I remember your name.
The music we play is Pythagorean because it's based on the scale as far as its melody is concerned. It's based on the chords that come from those simple numbers as far as its harmony is concerned. And its rhythm, in most cases, doesn't go beyond the number 4. Pythagoras found this a remarkable discovery because it showed him that what the ear hears as most satisfying and most restful, those simple intervals, are also the simplest numbers of mathematics. To him, this seemed a revelation that there's something underlying the universe which is attainable by us, both through music and through mathematics. For Pythagoras, music is a metaphor for the way the world works. Everywhere we look, we see the interplay of concord and discord, the interplay of harmony and disharmony. We see people and things coming together like the notes of a fugue.
Two and a half thousand years after Pythagoras formed his own academy in Crotone, his name is still taught in the local school, as it is in schools throughout the world. But it's not Pythagoras' belief that the world is number, or his discovery that music is mathematical that is taught. Rather, his name is associated with geometry and a theorem about triangles. If mathematics is at the root of music, we can imagine Pythagoras wondering whether it was at the root of everything.
Pythagoras.
And so he looked to the other senses, to the world of sight, to the world of vision, to geometry, to find a parallel numerical relationship to the one he had uncovered in music.
Teorema di Pitagora vuole dimostrare che A.
And that is exactly what the Pythagoreans believed they had found with their famous theorem. For as every schoolgirl and boy knows, the Pythagoras theorem states that the square of the longest side of a right-angled triangle is equal to the sum of the squares of the other two sides.
It is nice and dandy to say that the world is made up of numbers. It is an entirely different matter to show what that means. To show what that means is to prove the underlying numerical relationships that are responsible for the phenomena.
For us, proofs are something we learn at school. But for the Pythagoreans, they were a radical new discovery. Not only had they demonstrated that the world was based on number, but through proof, they believed they'd discovered the key to the hidden secret world that governed the universe.
Proof was precisely the means that gave one access to the underlying reality, to the substance that made up the cosmos.
We live in a world of geometry just as much as we live in a world of numbers. We surround ourselves with right angles and straight lines. Almost every object around us is symmetrical and made from elementary geometrical shapes. For us, shape and number are quite separate. In Pythagoras' world, they were inseparable.
And we can demonstrate it here by setting it out like this. If we draw
Keith Critchlow argues that we've much to learn from the aspects of Pythagoras we have discarded, and is the architect responsible for completing the largest Gothic cathedral in the world, St. John the Divine, on the fringe of Harlem in New York City. We tend to think of shape as an aesthetic matter, but for Pythagoras, shape, like music, was number.
Pythagoras believed that the world could be explained in terms of mathematics. The world we see and experience had inside it mathematical form. The way we believe he did this was to say that the number one could be treated as a point. A geometric point is the number one. Number two could be represented by two such figures, and that is the definition of a line. 2 points making a line. So the first relationship is a line. By bringing in the number 3 and 3 points, we get the first shape, a triangle. Now we can bring in the fourth one to make a square by doing this, or we can make it into a pyramid by putting the fourth one on top, and we get our first pyramid.
So Pythagoras associated numbers 1, 2, 3, and 4 with basic shapes: the circle, the line, the triangle, and the square. And for him, these numbers, these shapes, made up the world.
The history of architecture could be seen to be the history of employing these basic shapes that Pythagoras proposed. If we look at this skyline here, what do we see? We see nothing but geometry. May be occasional tree, but nearly a complete landscape of geometry. It is both its blessing and its disaster. Pythagoras would have been disappointed, let's put it like that, with New York. He would have been disappointed because he said there are 3 shapes which need to be used in harmony: the circle, the triangle, and the square. Now, if we look at this landscape, we see a complete lack of the circle and very, very little of the triangle. Pythagoras proposed that these had a psychological value. Now, the difference between New York we're looking at and the cathedral we're standing on is the cathedral embraces these shapes. It is fundamental to a cathedral, which is a building about the whole. That's what it sets out to be. It is and has to employ these shapes. And that's why a building like the cathedral is a vital necessity to New York. In a sense, the skyline of New York is Pythagorean in the geometric sense. And there are examples within what is basically a right angle and an upright geometry, where we see things like the Empire State Building, which is immensely beautiful because there's a change in shape And there's other buildings, one or two in the skyline, and they fulfill another very important role that Pythagoras suggested. It seems strange to us, maybe a little unlikely, but he said that these basic shapes must be kept in balance. Well, the evidence is right the way through architectural history, through the Renaissance, through Gothic England and France. They always employed these basic shapes in combination, and they were healthy at that point. So one could suggest there is the implication of being unhealthy if you only use one shape and you do not harmonize with the other shapes. So another reason why the cathedral here and the dome on the cathedral and what the cathedral will finally be will be an immensely important addition to the whole body, the geometric body of New York.
From our modern perspective, Pythagoras' view of numbers, if we can catch sight of it, strikes us as mystical and somewhat unlikely. But it is at the source not only of how our world looks, but how it works. For it is at the basis of our technology and our science. According to Dr. Atkins, a physical chemist working at Oxford, there's no doubt of our debt to Pythagoras.
Pythagoras opened the eyes of the world. He had a hunch, and it was little more than a hunch, that mathematics would prove to be the key to the description of nature, the description of everything around us. And in the course of 2,000 years, we've come to see that mathematics is the key to understanding just about everything. Pythagoras had the hunch, but it was Newton who turned it into the extraordinary edifice that we have today. Newton was really the first person to show that mathematics could be used to describe the world. He invented the mathematics that he needed as he went along. Well, I would almost take the view that he discovered it. The mathematics was around, and he prized it out of the universe. Take this game of croquet, for example. It might not look like mathematics, but you can describe its motion using mathematics. The speed of the ball, its position, the direction in which it's traveling, and its mass, the impact of the mallet on the ball. All these things can be summarized once and for all in a single, very simple mathematical expression. Essentially that the force is equal to the mass times the acceleration.
The history of science has been the development of laws that have uncovered the numerical relationships between things, which Pythagoras had only guessed existed.
Mathematics is a kind of very concise picture of the landscape. When you look at the pattern in which a tree grows, it's almost as though you see the mathematics forcing itself on your attention from inside the fabric of the universe. We see the way that a plant grows, that a flower opens. In each case, we find that it represents a particular type of mathematics. You may think that maths can never come up with the unexpected, so how can it possibly account for the rich complexity of the world that surrounds us? How can it account for the complexity of trees and of flowers and of people?
But mathematics is capable of generating unexpected things, as we can see in this pattern, in which each point represents a number, and the color, the speed with which the numbers multiplied by themselves approach infinity. Although generated by a simple rule, the pattern contains almost limitless complexity.
Keep in mind the general shape of these two big spheres with little lumps growing on them. And as I proceed, you will see this pattern appearing time and time again. What I'm going to do is to magnify the region inside that rectangle. You can see that we've still got the black and the blue regions, but that the structure on the line is becoming clearer. I'll do that again. I'll calculate the area within the rectangle, and you can see the complexity that's embedded in the complete diagram beginning to appear. Let me magnify this region, and we're getting the complexity unfolding in front of us. This is quite unlike an abstract painting. If you look at an abstract painting, what happens is that by the time you get to the magnification that shows the flakes of paint, you really lose all interest. But here, I can go on exposing the structure of this extraordinarily beautiful picture 1,000,000 times, or endlessly.
So although the complexity of nature does not look as if it could be generated by mathematical rules, patterns like this show that simple numerical relationships, repeated endlessly, can produce quite unexpected results.
Pythagoras had a vision. He had the vision that mathematics was the right way of describing the world. Indeed, he thought it was probably the only way of describing the world. But he went beyond that, and he had an extraordinary view that maybe the world was only mathematics, that all the leaves in the trees and the animals, the planets, they were just mathematics, nothing more than mathematics. Everyone thinks of matter now as being composed of atoms, but the closer we look, the less there seems to be. That the atoms become almost replaced by mathematics as we peer into them. So if I were to ask anyone what they meant by substance, they might say it's stuff that you could touch. And I might press them to go a little further, and they might say, well, it's a collection of atoms. But why should I stop there? Why don't I press them even further? And then they will say, well, it's made of electrons. They might say, well, it's made of nuclei. So I can go on pressing. But when I press them to the point of saying, what do you mean by a proton? What do you mean, really, truthfully, deeply, by an electron or a quark? All they can do is not say, well, it's a little piece of rock in the middle of it all. All they can do is to point to a collection of mathematical expressions and say, this is what I mean. And the question that may seem weird, but I think is not absurd, is the question that Pythagoras himself raised 2,000 years ago, that as well as just being a description, is it perhaps the case that when we touch this object, we're really touching the mathematics? That is mathematics the deep structure of the world?
For Pythagoras, mathematics uncovered the divine order of the world. And today, in Crotone, a Christian procession celebrates a similar belief in a divine order to the world. But it was Plato who extended Pythagoras' world of numbers to politics and religion.